In the world of automotive engineering, we often celebrate the triumphs, the engines that revolutionize the industry, set new standards, and push the boundaries of what's possible. But today we're taking a different journey. We're exploring the mechanical misfits, the engineering experiments gone awry, and the designs that didn't quite hit the mark. These are the 20 least reliable car engines of all time, a testament to the challenges of innovation and the complexities of automotive design. But before we begin, if you're new to the channel, please consider subscribing for more content like this. Number 20, Ford Cologne V6 2.8-liter. Our journey begins with the Ford 2.8-liter V6, an engine that exemplifies the struggles of the American auto industry in the 1970s. This power plant was Ford's answer to the fuel crisis, but it fell short in many respects. This V6 utilized a solid lifter valve train, a design choice that, while simple, resulted in a notoriously noisy operation. The constant clatter was a hallmark of this engine, a symphony of mechanical imperfection that owners quickly learned to recognize. But noise was the least of its problems. The real Achilles heel of this engine lay in its cylinder heads. Prone to cracking under thermal stress, these heads became the bane of many a mechanic's existence. The frequent failures were not just inconvenient, they were a testament to the challenges of designing engines for a new era of fuel efficiency. Number 19, Chevrolet 2.2-liter inline-4. As we move into the 1990s, we encounter the Chevrolet 2.2-liter inline-4, a pre-Ecotec engine that left much to be desired. This power plant was Chevrolet's foray into the world of compact, fuel-efficient engines, but it proved that the path to progress is often paved with setbacks. It was plagued by a host of issues, chief among them being frequent head gasket failures. These failures weren't just inconvenient, they were often catastrophic, leading to coolant leaks that could destroy an engine if not caught early. It was a harsh lesson in the importance of robust sealing technology in modern engines. But the problems didn't stop there. The engine was notoriously underpowered for the vehicles it was placed in, leading to increased stress on components. This stress often manifested in blown head gaskets and corroded freeze plugs, issues that became all too familiar to owners and mechanics alike. Number 18, Mazda Miller Cycle V6. Innovation is the lifeblood of the automotive industry, but sometimes cutting-edge technology can be a double-edged sword. Such was the case with Mazda's Miller Cycle V6, an engine that promised much but delivered a host of headaches. The Miller Cycle engine was a bold attempt to increase efficiency by using a unique supercharging approach. In theory, it was brilliant, a way to extract more power from less fuel. In practice, however, it proved to be a mechanical Pandora's box. The supercharger, crucial to the Miller Cycle's operation, was prone to failure. When it went, it often took the engine with it, resulting in repairs that could make even the most stoic car owner wince. But the problems didn't stop there. Excessive oil consumption was common, leading to additional engine damage if not closely monitored. Number 17, Pontiac Iron Duke 2.5-liter. The Pontiac Iron Duke 2.5-liter is a study in the challenges of adapting to changing market demands. Named for its robust iron block, this engine was designed to meet the growing need for fuel-efficient vehicles in the late 1970s and early 1980s. While the Iron Duke earned a reputation for durability in low-stress applications, it showed its limitations when pushed to deliver more power. As GM attempted to extract more performance from this modest power plant, its weaknesses became glaringly apparent. Rod knock became a common complaint, a telltale sign of bearing wear that could spell doom for the engine. Timing gear failures were another Achilles heel, with the plastic camshaft timing gears prone to wear. When these gears failed, they could cause the engine to misfire or fail completely. Poor oil flow was another issue that plagued the Iron Duke. Inadequate lubrication led to increased wear on crucial components, further compromising the engine's longevity. Number 16, Subaru EJ25. The Subaru EJ25 engine is a complex character in our narrative. On one hand, it powered some of Subaru's most beloved vehicles, earning a cult following among enthusiasts. On the other hand, it was plagued by issues that could turn ownership into a costly affair. Head gasket failures were the EJ25's most notorious problem. The combination of an aluminum block, thin cylinder walls, and inadequate head gasket material created a perfect storm for coolant leaks. These leaks could lead to overheating and, if left unchecked, catastrophic engine failure. But the head gasket wasn't the only weak point. The EJ25 was also known for excessive oil consumption, a problem that could sneak up on unsuspecting owners. If not monitored closely, low oil levels could lead to engine damage. Then there was the infamous piston slap, a condition where excessive clearance between the piston and cylinder wall would cause a distinctive knocking sound. especially in cold weather. While not immediately dangerous, it was a sign of accelerated wear that could shorten the engine's lifespan. Number 15. Volkswagen EA188 Diesel. The Volkswagen EA188 diesel engine represents both the promise and the pitfalls of advanced diesel technology. This engine was a showcase of VW's engineering prowess, featuring sophisticated systems designed to deliver power, efficiency, and low emissions. However, its complexity proved to be its downfall. The engine was plagued by a host of issues, many stemming from its advanced components. The turbocharger, crucial for the engine's performance, was prone to failure. When it went, it often took other engine components with it, resulting in eye-watering repair bills. But the turbo was just the tip of the iceberg. The piezo injectors, a high-tech solution for precise fuel delivery, were another weak point. These injectors were prone to failure, and replacing them could cost thousands of dollars. The balance shaft, designed to smooth out engine vibrations, was another trouble spot. Its failure could lead to increased vibration and accelerated wear on other engine components. Number 14. Jaguar V12. The Jaguar V12 is a prime example of an engine that was perhaps too ambitious for its time. This power plant was a marvel of engineering, promising silky smooth power delivery and the prestige that comes with a 12-cylinder engine. However, it was plagued by a host of issues that made ownership a costly affair. At the heart of the V12's problems was its cooling system. The engine produced an enormous amount of heat, and the cooling system struggled to keep up. This led to frequent overheating, which could cause warped cylinder heads and blown head gaskets. The electrical system, supplied by Lucas, often jokingly referred to as the Prince of Darkness by British car enthusiasts, was another weak point. Electrical gremlins were common, leading to starting issues and other irritating problems. But perhaps the most serious issue was the tendency for valve seats to drop out of the cylinder heads. This could cause catastrophic engine failure, turning a luxury car into a very expensive paperweight. Number 13. Mitsubishi 6G 72 3-liter V6. The Mitsubishi 6G 72 3-liter V6 is an engine that demonstrates how persistent reliability issues can undermine an otherwise sound design. Used in various Mitsubishi vehicles and adopted by Chrysler, this power plant gained a reputation for problems that could turn ownership into a constant battle against overheating and oil leaks. The 6G72's primary weakness lay in its cooling system design, which proved inadequate for the heat produced. This led to frequent head gasket failures, allowing coolant to mix with oil and potentially causing severe engine damage. For many owners, vigilantly monitoring the temperature gauge became a nervous habit, never knowing when the next overheating episode might occur. Oil leaks presented another persistent problem, particularly in high-mileage examples. Weak valve guide seals allowed oil to seep into the combustion chambers, leading to increased oil consumption and fouled spark plugs. The engine also became notorious for its noisy valve train, with ticking and tapping sounds serving as constant reminders of potential expensive repairs looming on the horizon. Despite these issues, when properly maintained, the 6G72 could provide smooth power delivery and respectable performance, its widespread use a testament to its potential and the valuable lessons it provided for future engine designs. Number 12. Chrysler 2.7-liter V6. The Chrysler 2.7-liter V6 is a prime example of how design flaws can turn an otherwise promising engine into a maintenance nightmare. This engine, used in a variety of Chrysler, Dodge, and Jeep vehicles, quickly gained notoriety for its tendency to develop engine-killing sludge. The root of the problem lay in the engine's oiling system. Poor crankcase ventilation and inadequate oil passages led to the buildup of sludge, which could clog vital oil channels. This starved the engine of lubrication, leading to accelerated wear and, in many cases, complete engine failure. Water pump failures exacerbated the issue. The pump was prone to leaking coolant into the crankcase, where it mixed with the oil to create a destructive sludge cocktail. This not only accelerated engine wear, but also led to cooling system failures. Timing chain failures were another common issue. The sludge buildup could affect the chain tensioner, leading to a loose chain that could skip teeth or break entirely. Number 11. Ford 1-liter EcoBoost. The Ford 1-liter EcoBoost engine represents both the promise and the perils of downsizing in modern engine design. This tiny 3-cylinder engine was designed to deliver the power of a larger engine with the fuel efficiency of a much smaller one. However, a critical design flaw turned this innovative power plant into a reliability nightmare. The fatal flaw in the 1-liter EcoBoost lay in its oil pump drive belt. In a baffling design decision, this belt was submerged in engine oil. While this might seem like a good idea for lubrication, it led to rapid degradation of the belt material. When the belt failed, it could cause sudden and catastrophic loss of oil pressure, leading to complete engine failure. But the problems didn't stop there. The engine was also prone to coolant loss, which could lead to overheating if not caught early. The turbocharger, crucial for the engine's performance, was another potential failure point. Number 10, Ford Triton 5.4-liter V8. The Ford Triton 5.4-liter V8 is an engine that demonstrates how even well-established designs can fall victim to flaws. This engine, used in many of Ford's popular trucks and SUVs, gained a reputation for reliability issues that could turn routine maintenance into a mechanic's nightmare. One of the most infamous issues with the Triton 5.4-liter was its tendency to eject spark plugs. The aluminum cylinder heads used a relatively small number of threads to secure the spark plugs, and these could wear out over time. In some cases, this led to spark plugs literally blowing out of the engine under pressure, causing significant damage. Conversely, when it came time to replace the spark plugs, owners and mechanics often found them nearly impossible to remove without breaking. This turned a simple tune-up into a costly and time-consuming ordeal. The engine's variable valve timing system was another trouble spot. The cam phasers, which control valve timing, were prone to failure. This could cause rough idling, loss of power, and decreased fuel economy. Despite these issues, the Triton 5.4-liter V8 was a workhorse engine that powered many of Ford's most popular vehicles. Its problems led to improvements in later versions, demonstrating Ford's commitment to refining and improving their designs. Number 9, BMW N63 V8. The BMW N63 V8 is a prime example of how cutting-edge design can sometimes lead to cutting-edge problems. This engine, featuring a hot V design with the turbos nestled between the cylinder banks, was an engineering marvel. However, it quickly gained a reputation for reliability issues that could turn BMW ownership into a costly affair. The root of many problems with the N63 was heat. The hot V design, while innovative, created an extremely hot environment for many critical components. This led to accelerated wear on parts like valve stem seals, which could fail prematurely and cause excessive oil consumption. The high heat also took its toll on the engine's timing chain. The chain could stretch due to the extreme temperatures, leading to timing issues and potential engine damage. In some cases, the chain guide rails could break, causing catastrophic engine failure. Turbocharger failures were another common issue. The turbos, subjected to extreme heat cycles, could fail prematurely, leading to loss of power and expensive repairs. Despite these problems, the N63 was a groundbreaking engine in many ways. Its compact design allowed for better weight distribution in BMW's larger vehicles, and when functioning properly, it delivered impressive performance. Number 8. Cadillac HT4100. The Cadillac HT4100 engine stands as a cautionary tale about the risks of rushing new technology to market. Introduced in 1982, this engine was Cadillac's answer to stricter fuel economy standards. However, its innovative design proved to be its downfall. It used an aluminum block with iron cylinder heads, a combination that promised lightweight and good heat dissipation. However, the different expansion rates of these materials led to serious sealing issues. Head gasket failures were common, allowing coolant to mix with the oil. This coolant-oil mixture created a sludge that could clog oil passages, leading to inadequate lubrication and accelerated wear on crucial components like crankshafts and camshafts. In many cases, this led to complete engine failure. Adding to the engine's woes was its electronic fuel injection system, which was prone to failure. This could cause poor performance, hard starting, and other drivability issues. Despite its problems, the HT4100 represented an important step in Cadillac's transition to more fuel-efficient engines. The lessons learned from its failures informed the design of subsequent engines, ultimately leading to more reliable and efficient power plants. Number 7. Triumph V8 3-liter. The Triumph V8 engine is a fascinating study in the challenges of developing a new engine from scratch. This British power plant, designed for use in Triumph's luxury sedans and sports cars, was an ambitious project that unfortunately fell short in many areas. At the heart of the Triumph V8's problems was its cooling system. The water pump, crucial for maintaining proper engine temperature, was poorly designed and prone to failure. This led to frequent overheating issues, which could cause severe engine damage if not addressed promptly. But the cooling system wasn't the engine's only Achilles heel. The head stud placement was a particular source of frustration for mechanics. The combination of perpendicular and angled studs made removing the cylinder heads an exercise in patience and skill, especially once the engine had been subjected to multiple heat cycles. Number 6. Ford 4.2-liter Essex V6. The Ford 4.2-liter Essex V6 is a prime example of how seemingly minor design flaws can lead to major reliability issues. This engine, primarily used in Ford's F-150 pickup trucks, quickly gained a reputation for problematic intake manifolds and head gaskets. The intake manifold was perhaps the engine's most notorious weak point. Its design led to frequent coolant leaks, which could result in overheating if not caught early. In some cases, coolant could leak into the combustion chambers, causing hydrolock and potentially catastrophic engine damage. Head gasket failures were another common issue. These failures often allowed coolant to mix with the oil, creating a destructive sludge that could clog oil passages and accelerate wear on crucial engine components. Number 5. Chevrolet Vega 2300. The Chevrolet Vega 2300 engine stands as a cautionary tale in automotive history, showcasing the pitfalls of pushing new technology too far, too fast. This aluminum block engine was revolutionary for its time, promising lightweight and good fuel economy. However, its execution left much to be desired. One of the Vega engine's most significant issues was its lack of cylinder liners. The high silicon aluminum alloy used for the cylinder bores wore quickly, leading to excessive oil consumption and reduced performance. This problem was exacerbated by inadequate cooling, which could cause the engine to overheat and warp. The cooling system itself was another weak point. Overheating was common, leading to warped cylinder heads and blown head gaskets. These issues could cause coolant to mix with the oil, creating a destructive cocktail that accelerated engine wear. Number 4. Cadillac V864. The Cadillac V864 engine is a prime example of technological ambition outpacing practical application. This engine, featuring cylinder deactivation technology, was far ahead of its time. However, the technology of the early 1980s simply wasn't up to the task of making it work reliably. The core of its problems lay in its cylinder deactivation system. The engine could run on 8, 6, or 4 cylinders, depending on load, theoretically providing V8 power with better fuel economy. However, the primitive computer technology of the time struggled to manage this complex system effectively. The result was an engine that often hesitated, stalled, or ran roughly. The solenoids controlling the rocker arms for cylinder deactivation were prone to failure, leading to erratic performance. Many owners ended up disabling the cylinder deactivation system entirely, defeating its purpose. Number 3. GM 3.6 High-Feature V6. The GM 3.6 High-Feature V6 is a study in how seemingly minor issues can cascade into major reliability problems. This engine, used across a wide range of GM vehicles, gained notoriety for its timing chain problems. The root of the issue lay in the timing chain's design and the materials used. The chain had a tendency to stretch over time, which could cause it to skip teeth on the sprockets. This would throw off the engine's timing, leading to poor performance, decreased fuel economy, and in some cases, catastrophic engine failure. Compounding the problem was the engine's direct injection system. While innovative, it could lead to carbon buildup on the valves, potentially exacerbating the timing issues and causing additional performance problems. Number 2. Cadillac Northstar V8. The Cadillac Northstar V8 is an engine that epitomizes the phrase flawed genius. This power plant was incredibly advanced for its time, featuring all aluminum construction, dual overhead camshafts, and 4 valves per cylinder. However, it was plagued by a critical design flaw that tarnished its reputation. The Northstar's Achilles heel was its head bolt design. The bolts were too short and had too few threads engaging the aluminum block. This led to a tendency for the head bolts to pull out of the block under the stress of normal operation, causing head gasket failures. When the head gasket failed, coolant could leak into the oil passages, leading to overheating and potential engine failure. The repair was notoriously difficult and expensive, often costing more than the value of older Northstar-equipped vehicles. Number 1. Oldsmobile 350 Diesel. At the top of our list sits the Oldsmobile 350 Diesel, an engine that stands as a stark reminder of the perils of hasty engineering. Born out of the need to meet stricter fuel economy standards in the wake of the 1970s oil crisis, this engine was essentially a converted gasoline V8 that was ill-prepared for the rigors of diesel operation. The fundamental issue with the 350 diesel was its lack of robustness. The head bolts, designed for a gasoline engine, were not up to the task of containing the higher compression ratios of a diesel engine. This led to frequent head gasket failures, allowing coolant to mix with the oil and causing catastrophic engine damage. But the problems didn't stop there. The fuel injection pump, a crucial component in any diesel engine, was prone to failure. When it went, it could send metal debris throughout the entire fuel system, necessitating extensive and expensive repairs. The crankshaft, another carryover from the gasoline engine, was prone to breaking under the increased stress of diesel operation. This could result in total engine failure, often with little or no warning. There you have it, the 20 least reliable engines in automotive history. These mechanical misfits remind us that behind every great car is a great engine, and behind every terrible car is probably one of these. Next time you're cursing your check engine light, just remember, it could be worse. You could be driving one of these oil-burning, wallet-draining, tow truck-summoning nightmares. Now, if you'll excuse me, I need to go check the oil in my